Well, the good news is we've gotten all the, what I think is the easy, probably somewhat uninteresting stuff out of the way. And now we're talking about some things that I think are really cool. Elements of secure design. How do you create applications that are properly architected? How do you start building something from the ground up instead of just identifying the issues after something's already built? Right? So that's the goal of this. So identify common elements of secure architecture and design, and then tie those principles back to what we've learned, the application security stuff. So these are the elements of secure design: authentication, authorization, data confidentiality and integrity, non-repudiation, and auditing and availability. In terms of authentication, authentication is identifying a user to a system. And there's several different ways to do this in theory as well as in practice. In theory, we have a few different ways. We have something you are, biometrics, right? That's the retinal scans, the handprints, the thumbprints. Something you have, which is like your phone, your RSA secure ID token, and something you know, password. And the more authentication mechanisms that we use, and if we use more than one method, then that ties back to that defense in depth. Because each of these has issues. There's reasons why or how an attacker might be able to bypass one of these. Take some of the picture identification stuff, right? The new phones where it's like, hold it up to your face and it'll unlock. What happens if you hold that up to a picture of a person, right? Would it unlock? Would it recognize the features of that face and say, yeah, that's the right person? Or what if it doesn't? What if you're at the airport and somebody says, hey, we want to open your phone. And now instead of having to ask you for your password so they can get in there, all they have to do is hold it up to your face, right? Now they've got all your information. So the way that we complement this is by using multiple of these features. So we could tie that facial recognition in with a password. And now I have to actually scan my face and enter a password, and now they can't do that. In practice, there's basically 3 different ways that we're going to use this, at least from a web application standpoint. HTTP basic, which is an HTTP protocol level authentication method, relatively insecure. It relies on MIME or base64 encoding of values. The bonus is it's available pretty much on all major web servers and browsers. So we have the ability to do this basic authentication. We have NTLM, which is more secure. It uses a challenge and response method. But it's mostly Windows, IIS, Internet Explorer specific. So if you're using a different browser or a different platform, Apache, Linux, something like that, it probably won't work. And then we have the most common, which is form-based authentication. So we've got support for form-based authentication pretty much every platform that we're going to use. And the nice thing with form-based authentication is you can usually write your own code, and now it'll work with legacy systems and things like that as well. In terms of authorization, the definition of authorization is we're looking at what resources a user should have access to and what the user is supposed to be able to do within the system. So we're trying to figure out what can they do and what shouldn't they be able to do. And this is where we want to keep in mind that default to not. By default, users should be able to do nothing. Now let's start from there. Let's figure out what they can do. And both Java and ASP have schemes for accomplishing this, which is better than writing your own if you can get away with it, right? Because people do silly things. Some people know more than others. So use vetted platforms. In terms of data confidentiality and integrity, we usually accomplish this with cryptography. And so we have crypto techniques that are useful in application security. We have things like symmetric cryptography, public key cryptography, or asymmetric cryptography, and we have hash functions. And protecting data when in storage helps to provide defense in depth. When Dan talked about the SQL injection, if you can just run a SQL injection exploit and get back all the data, it's game over. Well, what if that data is encrypted, right? If if the data is encrypted, well, now somebody has to break the encryption. They have to figure out how do I get the key to decrypt the data. So by layering our defenses, by doing this defense in depth approach, we're able to protect against these things. In terms of cryptography, cryptography is processing data in such a way that's rendered into an unintelligible form, but can be recovered without data loss. And we always, always, always want to use well-tested, industry-standard cryptographic routines rather than write our own. We never create our own cryptographic routines because it's effectively security through obscurity. It's way less useful than having a whole lot of really smart people build your foundation for it. Is there anybody in this room that's a crypto expert? Yeah, me neither, right? Cryptography requires a pretty decent background in mathematics. It requires a lot of extensive knowledge about how all of this stuff works. And even if you go online and you search like, how do I do symmetric cryptography, unless if it's, here's the functions that you should call, don't believe it, right? Because somebody else probably wrote that and they probably have no idea what they're doing. Symmetric cryptography is traditional cryptography. You have the same key that's used for both the encryption and the decryption. The cool thing about symmetric cryptography is it's really fast, right? If I'm using the same key for the encrypt and decrypt, I just run that key through the function, it goes both ways. And so we have triple DES and we have AES. Those are our industry accepted routines. Triple DES being phased out. So if you're going to do encryption, symmetric cryptography, use AES. Now, the problem with the same key being used on both ends is that that key, if compromised, it compromises both ends, right? And it makes it difficult to exchange keys. So if I want to give my key to somebody else, let's say I'm here and my wife's at home and I want to give her my key, what am I going to do? Am I going to just send it via email? Well, what happens if somebody looks at it via email? When I call her, somebody might hear it. So key exchange becomes a problem when we're talking symmetric cryptography. In terms of accomplishing our application security goals, we want to use it when we're protecting data that's provided to the system and used by the system in place. So if the same system is going to both take the data and use the data, that's where we want to use symmetric cryptography. So an example might be credit cards where it's stored for reuse with the customer account, or bank account numbers or social security numbers, things like that. So if it's going to be used by that same system, use symmetric cryptography. Public key cryptography, or asymmetric cryptography, is different. You have two keys. These two keys are mathematically related to each other. But you have one that's basically used for encryption and one that's used for decryption. And the truth is it really doesn't matter which one you use as long as you use the opposite key. But one is labeled as public key and one is labeled as private key, with the public being accessible to the public and the private being kept private. The problem with public key cryptography is that it's really slow because each of these keys are basically factors of prime numbers. Really, really big prime numbers. And so it's going to take a lot of time in order to calculate the mathematics around that. The positive thing about it is that key management is greatly simplified. Because if I'm trying to do a key exchange with my wife, and I want to send her something securely, I send her my public key. Or, I'm sorry, she sends me her public key if I want to send data to her. I now take her public key, I encrypt the data that I want to send to her, and I send it to her. Because it's encrypted with her public key, and she's the only person who has the private key, I can then send that on, and I know that she's the only person on the other end who can decrypt that information. Likewise, if I want her to be able to respond back to me, I send her my public key, she encrypts the data there and sends it back to me, and then I'm the only person who can decrypt it with my private key. Right? So key management is way easier because I can give everybody my public key because I don't care if you guys send me encrypted messages. I only care if you decrypt those messages because they're meant for me and only me. Right? So RSA is a good example of public key cryptography. In terms of accomplishing our application security goals, we use it to collect data that's provided to the system and then is used by other systems. So we use that public key on the systems that basically are encrypting the data, the systems that are maybe low trust, those web systems. We encrypt the data there and we stick it in the database. And so even if somebody were to compromise those systems and they get access to our public key, all they can do is encrypt data. They cannot decrypt data with that public key. So the public key is stored and used on our least protected systems. And then our private key is what's used to decrypt the data on our higher trust systems. That makes sense? Now the interesting thing is when it comes to web browsing, right? We hear about Ssl certificates all the time. Which do you think it uses?
Both.
Do you think it uses symmetric key or private key? I heard somebody say. What's that? Non-symmetric, asymmetric? It actually uses both. So, the public key cryptography piece is the certificate piece, right? That's the slow piece when we first initiate that connection, because I have to go and I get their certificate, and I validate their certificate, and I make sure that the data that I'm getting from them is correct. And we use that to effectively negotiate a key exchange. So once I know I'm talking to the right person, I can send them the information about how to talk back to me. And then from that point forward, we actually negotiate a symmetric key, because we want it to be a faster transaction. So we use the PKI, the public key cryptography, in order to set up the transaction, because that's the easy exchange. And then we use symmetric to continue that talk, because that's the fast exchange. So we use the two in combination when we're talking SSL. There's a third piece here which is called hashing. We talked a little bit about this when we were looking at the salts and how we store passwords. A hash function basically takes an input x and it turns it into a fixed length string according to some function, f of x. The qualities of a good hash function is it should be easy to compute and it should be hard to reverse, meaning that this is effectively a one-way hash. So somebody who has the data, who gets the data out on the other side, they're not going to be able to, without creating one of these complex rainbow tables, they're not going to be able to turn that data back into the original value. The other quality is that it's hard to find collisions. And a collision is where you have two inputs, so we throw two inputs, x and y, into this function, and we get the same output. What that means is that there's two possible solutions to that problem. Okay? And so we want as little of those as possible. You also hear these referred to as birthday attacks, where two people have the same birthday, right? That's the same kind of thing. SHA-2 family of algorithms are a good example for hash functions. MD5 and SHA-1, they have issues, they should be phased out. So how do we use hash functions to accomplish our application security goals? We avoid storing actual data when it's only needed in the future for comparison. So take your password as an example. Once you've entered your password into an application and you've authenticated with the system, is your password ever used from that point forward? No, right? Your password from that point forward turns into a session, and that session is what you use to stay authenticated with the server. So what if, instead of storing the password in the database, what if we hash the password? And then we store the hash because we know the hash is non-reversible. We don't go from the hash back to the original password. Well, now when we authenticate a user, they enter their password, we hash the password, and then we compare it to the hash that we have stored in our database. If the hashes match, then we know that they entered the same password that we stored earlier, right? Well, then we get into the whole rainbow tables thing that we talked about earlier. And that's why we have salts. And we have the salts for each of the users. And now we're hashing the password plus the salt and storing that. But in any case, it's something that we can calculate, but it's non-reversible. We never get back to that user had that password. If we can do that, then we have a significant problem. Other things that you might want to store as a hash, maybe you have social security numbers where you're only using it for identification, API keys, things like that. Non-repudiation and auditing. So secure applications need to provide the ability to determine what happened and what didn't happen. So the way we do this is with non-repudiation and auditing. Non-repudiation is the ability of a training partner to prove or disprove having previously sent or received some message to or from another person. So humans do non-repudiation. Computers help provide evidence to support those efforts. So the techniques we use to implement non-repudiation are what's called a digital signature, which I'll talk about in a second, and logs. Digital signatures simulate a manual signature. They say, I agree with what this document says. And so there's two operations with a digital signature. There's the signing, just like you would sign on a document. And then there's the verifying, which is saying that signature belongs to that person, right? And only that person. So the way we do this is with that asymmetric cryptography, the public key encryption. So here's the example. We have Alice on one side, and we have Bob on the other side. And Alice wants to send a message to Bob, and Bob needs to be able to verify that Alice is the person who sent that message. So what Alice does is she takes her message and she hashes it, the full message, which turns into that fixed length string, the unique string for her message. And once she has that hash, what she can do is she can basically encrypt that hash with her private key. Now remember I mentioned that those keys, the asymmetric keys, they go both ways, right? So I can encrypt something with my private key and it decrypts with my public key, or I can encrypt with my public key and it decrypts with my private key. We're going to encrypt it with Alice's private key. Now Alice is the only person who has that private key. But anybody can get her public key. That's publicly accessible. So then Alice goes, and she sends along the message to Bob. We're not worrying about confidentiality. We're just worrying about saying that Alice is the one who sent this message. And then she sends along this signature. The signature is that hash encrypted with her key. So when Bob receives the message from Alice, he's able to look at the message, and to determine whether Alice did or did not actually provide this message, he looks at that signature. The way he does this is he hashes the message, and that hash is the same function that Alice used. Therefore, he should get the same result that Alice had when she originally had it. And then he takes that signature, he uses Alice's public key, because he knows that that's the public key that goes along with her private key, and he basically decrypts that, giving back the hash that Alice put in the box. And then Bob compares that hash that he got out of the box with the hash that he calculated, and he says, are these two the same value? If the hashes are the same, then he knows that Alice is the only person who could have possibly sent that message, because she's the only person who has her private key. If the hashes don't match, then he knows that somebody tampered with the message. It is no longer the same message that Alice sent. Does that make sense? Questions? I must be really good at this explaining things, because you guys are very quiet right now. All right. So, auditing. Audit logs preserve a record of when the events occurred and under what conditions they occurred. And as I mentioned earlier, one of the first things that somebody's going to that somebody's going to ask for if you're doing some sort of data breach investigation is, can I see the logs? Because you're going to use those logs to reconstruct the sequence of events that led up to that compromise. So we want to be careful about what we log, right? But we want to log enough information so that we can reconstruct those events. Why do we want to be careful about what we log? Well, you probably don't want to put passwords into the log. You probably don't want to put social security numbers into the logs or credit card numbers into the logs. There's no real point in logging those things. I once had a developer who would basically, he wrote an app that interfaced with the database. And he would read the database information from the config file. He would then connect to the database, and if the connection was successful, he wrote the database username, password, database name, and host name into the log file. So when I was going through the log file, one of the searches I ran, you guys can run this in your environment too if you do logging, look for the password for your database. And if it shows up in the log, you got a problem. Because now that's data, sensitive data exposure. Okay? Other people are seeing that. That shouldn't. In Windows, you can use event log, or you can log to files. Availability. So secure applications have to be available for legitimate users to access. When we talked earlier, it was CIA, confidentiality, integrity, and availability. This is largely dependent on hardware and software configurations. So this is where we start talking about, on the application level, input validation. Right? We want to guard against those buffer overflows and those kind of attacks that might take our application down. It also means proper error handling. Because if an application gets put into an inconsistent state, we've got issues. It means val open and val close, deciding, hey, we ran into this condition. How do we treat this? What do we do here? Because we want our application to be online and available for our customers to use. Now, at other levels, talk about system level and things like that, it might be multiple servers and load balancers and things like that. So that's the end of that section. And the last little bit here is threat modeling. Now, threat modeling is something that can be incredibly useful, but we don't do it often enough. So the goal of this section is to introduce you guys to threat modeling. We'll talk about how do we apply some of these concepts to application security. And we probably won't participate in an example threat modeling exercise. One, because we really don't have time, and two, because nobody wants to get up here in front of a bunch of strangers and say, here's my application, let's stare and talk. But it's definitely something that you should take back to your organization and say, hey, we're doing this new application thing, let's threat model. Let's see if we can't figure out if there's areas that might be worth improving. So, the thing about threat modeling is it should be done as early as possible. Maybe even before any code is actually written. Michael Howard is the guy who wrote the book on writing secure code. Worked at Microsoft, security manager over there. Really sharp guy. And he said that if I could do any activity to help application security, he said I'd threat model every day of the week. So it's something that's incredibly important and incredibly useful, but it does save some time. And Michael told us about the story. They were working on a new thing for Windows. This was years ago. I think he called it Castle, if I remember right. And it was this architecture where you had kind of like the keys to the kingdom, and think of it like a castle, where all the keys are basically surrounded by the castle, right? And then you would have all these other processes that had to communicate with the castle and basically request to get things out. And as they were doing this threat modeling activity, they were kind of understanding the pitfalls of this approach. They started to realize, before they ever built the application, before they wrote the code, they started to realize, hey, maybe this isn't such a good idea. You know, if an attacker can just bypass it this way, then what's the whole point of doing all this stuff? Why are we putting the extra burden on the users? And so, as a result of the threat modeling exercise, it actually dropped that product. So we can use threat modeling to find security defects before the code is actually written. These are the steps in threat modeling, and I won't go through these, we'll go through each one individually. So the first step here is to define our use scenarios. How will the application be used? What types of users are going to use this? Under what circumstances are they going to use our application? Let's consider some examples. What about an insider threat? What about for a mobile device? What happens if that device gets stolen? Not the same thing as use cases. From there, we list external dependencies. what things outside the application are required for our application to run. So this might be a web service. Maybe our application makes a RESTful web query to something, pulls back some data in order to do some operation. Maybe it's a SQL database or a message queue, right? So we have to know, in order to properly model our application, we have to know all the things that our application interacts with. Even if we don't own it, even if we didn't write it, we have to understand what those things are. We also have to understand if there's any sort of environmental issues like operating system configurations that we're relying on for security. What about particular browsers or versions of browsers? Is there functionality that is outside of the scope of our application that we're using to ensure that our application is being protected? We write those down. Then we go and we define our security assumptions. What assumptions are being made about security? Are we relying on certain things that aren't part of our application, but are there in order to keep us safe, in order to keep the data safe? Maybe there's a data protection API, or we're using access controls on files in order to make sure that somebody doesn't do something bad. And we have to define those. We have to make those explicit assumptions, because if we're going to keep this platform up and running and safe, they need to be explicit. So then, we create external security notes. We document the dependencies and assumptions for our end users. And we use this to understand what we're modeling and what we're depending on. So what are the things that we're going to look at here, we're going to actually threat model, and what are the things that are kind of outside the control of our application, but we require them in order for our application to work, kind of defining scope, right? So here we have our stack. And we have everything from our network card to the drivers that run the card to our TCP/IP stack, which is in our operating system, the IIS, a web server, to ASP and .NET, the frameworks. Then we have the libraries that we're using, and then we have our application. And what we've learned through this step is that everything below my library is something that we're relying on. We depend on it. There's implicit requirements on the security of those components. We've probably made some assumptions about those things, but we can't really do anything about them. So we assume that IIS is properly configured, right? We assume that IIS is configured to not show a list of all files in a directory. That would be a security assumption. We assume that IIS has HTTP basic authentication to prevent somebody from accessing this directory. That would be a security assumption. Now, everything above that, my library, my application, that's in our scope. So we are going to threat model those things. And most of the time when we talk about threat model, what we're actually talking about is a data flow diagram. So we're taking the information about our application and we're turning it into a picture. The cool thing about this is a lot of times application flow, these maps, don't exist within an organization. So you're actually defining and creating something that's valuable beyond just the security aspect of this. So we have effectively 6 things that we're going to mark out here on our data flow diagram. We're going to create a box, and that's going to be an external interactor. Something outside our system that's going to interact with our system. Or something outside our system that we're going to interact with. We have an arrow, and arrows can go multiple directions. Those are our data flows. And usually we'll label those arrows with what type of data is going over there. Right? We have 2 lines. That represents a data store. And a data store could be a database, it could be a file system, right? The idea is this is some place where we're going to write some data to. We then have a process, which is represented by a circle, and a complex process, which is represented by 2 circles. A complex process is one that can be effectively decomposed into multiple singular processes. So we may have one complex process that's like my application, and will show flows going into and out of that application. But your application is really composed of something that does some input processing, and then something that sends data here and gets a response back, and then something that does output processing, right? Your application may be composed of multiple pieces. And then the last piece for our data flow diagram is we want to explicitly identify trust boundaries. Trust boundaries are areas where we go from something of lower trust to something of high trust. So think about your common website. The internet is probably an area of low trust. Your web server is probably an area of higher trust because you manage it. And so there's an implicit trust boundary between an internet user and your web server process, right? We want to change that from an implicit boundary to an explicit process boundary, and that's by labeling. So here's an example data flow diagram. What this is telling us is we have two external interactors. We can see the box on the left and the box on the right. On the left, we see the external transaction source. On the box on the right, we have some external processor. And as we follow through this diagram, we start to get an idea of what's happening here. We have an external source. It is sending some incoming transactions to a processing application. That processing application then sends some transactions to handle externally to this external processor. External processor does something. It then sends back a transaction status and a response. Our processing application then goes from there and it sends some data to a log. In this case, it's our application logs. It then stores some data in the database and retrieves some data back from the database. And then the last step is it sends a transaction status and response back to the original external transaction source. We've also identified two trust boundaries in here. We have a trust boundary between the external transaction source and our application, and we have a trust boundary between our processing application and the external processor. One could argue that there's another trust boundary, possibly two, between the processing application and that Oracle database. Probably depends on whether that database is local or not, right? If it's local, maybe, maybe not. If it's external, then that database probably does have a trust boundary because we're probably going to have to authenticate with it. We're going to have to make sure that we are who we say we are when we communicate with it. Right? What do you guys think this is a diagram of? Come on, all day I've been talking to you guys. You guys talk to me. What do you guys think?
The processing application is some sort of medium.
Yeah?
One is the source. Is it a credit card processing?
Yeah. I heard back there. Credit card processing. Right? So our processing application, our external processor, is a customer. Our customer is utilizing our application, and at some point they say, I want to buy something. So we have this external processor that's actually the credit card processor, and we send some information. We send them a transaction. And then they do some processing of that, and they send us back, was it successful or was it not? Right? And then from there, our application sends some data to the logs, probably saying, hey, we got a positive response back from this request. And it stores some data in the database, which is probably like, hey, we got this order, right? Here's the part that they ordered. And then it sends back the data to the customer saying, hey, we got your order, here's your order number, right? We store that in the database. That's probably what's going on here. So what we've seen is we've taken an application that none of us had any idea, well, none of you guys had any idea about what this thing did. And in a few symbols, one picture, you guys are able to ascertain what this guy is doing. You can look at this picture and say, hey, there's a couple of things that are outside this that are talking to us. And we probably need to do some additional things to authenticate those, to make sure we are who we say we are, and they're who they say they are. So the next step, once we create our data flow, is to determine the threat types. So Microsoft used what's called STRIDE. STRIDE is basically taking that CIA, the confidentiality, integrity, and availability, and expanding it. And so now instead of those, you get spoofing identity, tampering with the data, repudiation, information disclosure, denial of service, and elevation of privilege. Those should sound pretty familiar because we've talked about these throughout the day today, right? We talked about denial of service, we talked about information disclosure. So, now that we have STRIDE, we know of our different types of threats, we can identify how the threats, the different threats to the system. So we enumerate all the assets in our threat model, and certain types of threats only apply to certain types of assets. We can do what's called a threat tree. A threat tree basically describes the decision-making process an attacker goes through to compromise a component. It can also be described textually to act as a more concise method, but in this case what we have is we have a threat, spoofing a web server. It even says spoofing. So, to spoof a web server, it requires two things. One, we need to create a machine with the same name, and, you can see that little and up there, knock out a valid machine. Now, creating a machine with the same name, that doesn't require any special skill, right? Probably. So the threat that we're trying to do here is knocking down the valid machine. And what we do is we identify all the different ways that we could potentially do that. So we might do DNS hijacking. We might flood the server with bad IP packets. We might turn off power to the server. And we might rename the server. Those are all ways to knock out that valid machine. And in this case, we said, all right, turning off power to the server. What does that entail? Well, we could either have access to the power switch and turn it off that way, or we could turn off access to the computer room power switch, right? Power down the whole room. And from both of those, we determined that physical access to a restricted area is required, and that's probably not going to happen. So you can see the dashed lines effectively means that we've ruled out those threats. We're good. The last one here is renaming the server. And in order to rename the server, we need physical access to the computer, which requires, again, physical access to a restricted area. And so, therefore, we're not touching it. So, what we've decided via our threat tree is that in order to spoof a web server, there's really just two ways that we think that an attacker would do this. One is through DNS hijacking, and the other is to flood our server with bad IP packets. Now, just having that information helps us as defenders to try and figure out where do we put our eggs, which basket do we put our eggs in, right? So in this case, we want to figure out how do we prevent DNS hijacking and how we prevent the bad IP packets. Now, we talked about the STRIDE, the spoofing, tampering, and whatnot. So where do we go from there? We need to map threats to the different types of assets. In this case, we have external entities, we have processes, we have data flows, and we have data stores. So with this, we have our different threat types: spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege. And we go through and we say, these are the threats that apply to these assets. So in the case of an external entity, one of the threats that we need to be concerned about is spoofing. With somebody who is outside of our environment, something that we don't control, how do we make sure that they're who they say they are? And when we're talking to them, that we're talking to the right thing. We may also have the situation with repudiation, where we need to make sure when we tell them to do something, or they tell us they did something, how do you prove it? Right? Or, in the case of a data flow, we might have issues with tampering. What happens if somebody messes with that data flow and changes the data while it's in flight? That would be a problem. That affects the integrity of our application. So that's how we map the threats to the assets. Then we determine the risk. Now, the traditional way of calculating risk, if you study for your CISSP, is risk is the chance of an attack times the damage potential, or likelihood times impact. That's kind of subjective, right? How likely is it that somebody's going to exploit a cross-site scripting vulnerability on my server? Yeah, I think it's pretty likely. Right? We know about a cross-site scripting vulnerability, therefore somebody can probably find it. Pretty subjective. So dread is Microsoft's way of calculating the severity of existing vulnerabilities. And dread stands for damage potential, reproducibility, exploitability, affected users, and discoverability. So when it comes to the risk of something happening, these are the factors that make up that risk. You're no longer looking at how likely it is as just a singular value. You're looking at likely in terms of, is it discoverable? And is it reproducible? And you're not looking at impact, you're looking at damage potential and who's affected, right? So the last bit here is mitigations. Once we know about the issues, we know about the threats, we know how they affect our assets, we've identified the risk, now we have to decide what are we going to do about it. And the first answer is we can do nothing. We could accept that this is a problem and say we don't care about doing anything about it. And that's a perfectly acceptable answer if you have a proper risk acceptance process in place. That's where the simpler stuff comes in, right? You could remove the feature, right? We have a problem here. Let's just get rid of the problem, and we're done. You could turn off the feature, say it's there, but you've got to explicitly turn it on, so you're kind of taking fate into your own hands. You could warn the user and say, hey, this is a problem, you shouldn't do this, but if you do it, here's what's going to happen. Or you could cover the threat with technology. Maybe this is one of those situations where you say, yeah, that's a problem, we're just going to buy a WAF. Right? You got lots of money, you can throw a WAF in there, it's going to solve all your problems. Now, there's also some technical countermeasures for each of those items, each of the stride items. We've covered these. When it comes to spoofing, the way we mitigate against spoofing is authentication. Right? We want to prove that we're supposed to access this application, or this application is supposed to access us. We authenticate. If we want to make sure that data isn't tampered with in flight, then we provide integrity. If we want to make sure that an application doesn't go down, we don't have a denial of service, then we ensure availability. If we want to make sure that things are only supposed to do the things they're authorized to do, then we provide authorization, right? So we've talked about all this today. So here's one last example for you guys. This comes out of the Microsoft stuff, by the way. So in this case, we have an application called Integrity Check. An Integrity Check is a solution that monitors all of our client workstations. It checks for any file changes. There's a client app that's on the workstation. It gets installed by a CD. And then there's a service on the server, but it doesn't have any sort of data stored. And then you have an admin app on the admin workstation that kind of administers all this stuff. So when we start with our data flow, what we basically have here is an external interactor, a couple of data flows, and a complex process. Our external interactor is the administrator, a person. The administrator sends some analysis instructions into our complex process. That's the integrity application. And then the integrity application responds back with some resource integrity information. That's all we know at this point, but that's actually a lot of data. We've got a lot of information about this. So now what we do is we take that complex process and we decompose it. We take it a step further. And once we do that, we see something like this. We still have our admin. Our admin is still sending instructions into this thing, but it's now not just this integrity application, it's the integrity admin console. We have a process for that. In our integrity admin console, we can see send some commands to the integrity host software. And that host software has access to raw registry data pulling out of the registry, as well as raw file system data pulling out of the file system. And then it sends that resource integrity data back to our admin console. Our admin console is pulling some settings out of the config data. It's going to read some information from the integrity files and then update some information. And then it's going to send some data back to our admin. Well, that's interesting, right? Because we can now see we've got multiple data stores here. We've got multiple trust boundaries. We have our integrity admin console that's talking to the integrity host software. And that's probably happening over a network. Therefore, there's probably a trust boundary there. Well, if there's a trust boundary, how do we want to fix that? How do we fix the spoofing piece of that? Authentication, right? So we know we have to authenticate there. Then we have this integrity host software. The integrity host software is doing something here where it's grabbing raw registry and raw file system. That requires elevated privileges. Well, with privilege elevation, how do we fix that? Authorization, right? So we know a lot more data about what's happening here, and we can make some decisions about how do we architect this. What are the pieces that we have to put into this puzzle in order to make it secure? And we know this without even seeing one line of code. That's pretty powerful, right? All right. 2 more slides and then we're done. First one, why do we want threat modeling? This is an interesting graph. If used properly, threat modeling helps development teams to identify potential threats, make decisions before any vulnerable code is written. And addressing security bugs early is much cheaper than addressing them later. So what you see here, that blue line, is the percent of defects that are introduced in each phase. And granted, this is waterfall, and most people these days are doing some sort of agile methodology, but it's still very indicative of that. Most of the defects, 85% of the defects, are introduced during the coding phase. And then after that, maybe a little bit when you're doing some field testing and post-release and whatnot, but not so much. The orange line is where we're finding the defects. And what we see is we're finding more of the defects as we move to unit testing and functional testing, eventually to field testing, and not so much in the post-release, right? So we're introducing defects early, we're finding them later and later. And then that red line is how much it costs to fix the defects in that phase. And it's an exponential curve as you move from coding into those later phases. So it's exponentially more expensive to fix a defect that's found in post-release, where we find most of the defects are going to be out there, right? Exponentially more costly than if we find it early. So by threat modeling, we're finding the stuff sometimes even before that coding phase. We're finding the stuff before the bugs are actually introduced, which makes it a much less cost-intensive process. Make sense? Yeah? All right, last slide for you guys. Security development lifecycle. So a lot of us are familiar with software development lifecycle, where we know how software works, how software gets built. And so you can kind of see along the bottom there, you've got like a requirements phase, and then the design phase, and then implementation, verification, release, and then support. Typical software development process. And we can kind of see above that how we get to those pieces. So in the requirements phase, we're creating feature lists, quality guidelines, and architecture docs, and whatnot. And you can see how each of those things get built, right? Security is the same way. If you involve security as part of your software development lifecycle, then they can help you in each of those stages as you go through the process. So when you're gathering the requirements and you're looking at how do we do this, they can do training, right? They can say, here's how we do secure web app development, just like we do today. We can look at security and privacy for this application. We can start, what kind of data does your application host? Does it have credit cards? Maybe we should have a conversation about that. We can start talking about cost and things like that. As we move into the design phase, we can start talking about design best practices. We can talk about some of the best practices we talked about earlier today. Maybe we do a security architecture and attack surface review, or we look at the risks that are involved with this particular application. As we move into implementation, now it's tools. How do we, what are the tools that we can use for best practices? What are testing practices that we can use? As we move into the verification, we're starting to get ready for production, right? So maybe it's incident response plans. What happens if this gets broken? Who do we talk to? How do we escalate? Maybe it's some final security push or pen test to verify that the application does what it's supposed to do. As we release, it's the final reviews. It's making sure, all right, did we cross off all of our T's? Did we dot all the I's? Are we in a good place? And then once it's out there, it's making sure that if there's an issue, that we're prepared to respond to. And this is one of the reasons why you start hearing of all the agile stuff, all the DevOps stuff. They start putting DevSecOps, right? Because security is really a partner with development. We're all in this together. If your application gets hacked, we're all spending late nights in the office trying to fix it. So security is a partner in all of this. And if you have questions about how something should work, if you have questions about how do we fix a vulnerability that we found, it's a team. We're all working together. Right? So, with that, I'll open it up to questions. If you guys don't have any questions, hope to see you tomorrow at LASCON. Yeah. Questions?
The slides, I noticed the last two sections, the architecture design and security architecture design, and this security section in the morning and not in the original, the link we provide.
They're not in the link that they gave? I may have edited it afterwards.
Yeah,
So you,
just inches.
yeah, I'm happy to give that out. Send me an email. I'm happy to do that. Any other questions? Yeah. All right. Thank you, guys.
Thank you.